This is the design project. My name is Chapman. Design constraints. A full wave rectifier is to be designed to produce a 5-volt output with a ripple of not more than 3%. Supply 1 ampere of current to the load using an input line voltage of 120 volts at 60 Hz. Key tasks. Find resistors, capacitors, and transformer turn ratio values for your circuit. Design, apply parts currently available from the commercial market. Using equations, calculate the peak diode current, the average diode current over the entire signal period, the inverse voltage that each diode must sustain. Verify the circuit using multisim and record your presentation with a video and submit your presentation materials and video. Our objective is to design a full wave rectifier to meet particular specifications. A full wave rectifier is to be designed to produce peak output voltage of 5 volts and deliver 1 amp to the load, and produce an output ripple of not more than 3%. An input line voltage of 120 volts at 60 Hz is available. A full wave bridge rectifier will be used. The effective load resistance can be found using the equation R equals the voltage of the output divided by the current of the load, 5 volts divided by 1 amp, producing a resistance of 5 ohms. Assuming the diode cut-in voltage is 0.7 volts, we can find the peak value of the voltage into the rectifier by using the equation Vs max equals the voltage out max plus 2 times the diode cut-in voltage, giving us 5 volts for the voltage output plus 2 times the diode cut-in voltage of 0.7, giving us a voltage into the secondary voltage of 6.4 volts. For a sinusoidal signal, this produces a root mean square voltage of 4.53 volts, and we find this by using the equation voltage of the secondary RMS equals voltage of the secondary peak divided by the square root of 2. To give us a value of 4.3 volts. The transformer turns ratio is then found using the equation turns of the primary over turns of the secondary equals 120 voltage of the primary divided by the voltage of the secondary. So we get a turns ratio of 26.5. For a 3% ripple, we use the equation voltage ripple equals 3% times the voltage output, 0.03 times 5 volts, and we find our ripple voltage is 0.15 volts. The required filter capacitor can be found by using the equation capacitance equals the voltage output divided by 2 times the frequency times the resistor times the ripple voltage. And that gives us 5 volts divided by 2 times 60 Hz times 5 ohms times 0.015, and that gives us a capacitance value of 55.56 millifarads. To find the peak diode current, we use the equation voltage max divided by resistance times the quantity 1 plus pi times the square root of 2 times voltage max over the ripple voltage. And that gives us a value of 26.65 amps as our peak diode voltage. To find the average current over the entire signal period, we use the equation 1 over pi times the square root of 2 times the voltage ripple divided by the voltage max times the voltage max divided by the resistance times the quantity 1 plus pi over 2 times the square root of 2 times the voltage max over the ripple voltage. And this gives us an average diode current of 1.078 ampere. Finally, to find the peak inverse voltage that each diode must sustain, we use the equation peak inverse voltage equals the voltage reverse max equals the voltage of the secondary max minus the diode cut-in voltage. So we get 6.4 volts minus 0.7 volts equals 5.7 volts. The minimum specifications for the diode in this full wave rectifier circuit are a peak current of 26.65 amps and an average current of 1.078 amps, and a peak inverse voltage of 5.7 volts. In order to meet the desired ripple specifications, the required filter capacitance must be large since the effective resistance load is small. The required capacitance for this circuit is 55.56 millifarads. A particular turns ratio was determined for the transformer. However, this particular transformer is probably not commercially available. This means an expensive custom transformer would be required, or if a standard transformer was used, then additional circuit design is required to meet the output voltage specification. A constant 120 volt input voltage is assumed to be available. However, this voltage can fluctuate, so the output voltage would also fluctuate. Since we simply used an assumed cut-in voltage for the diode and used approximations in the development of the ripple voltage equation, we can use multi-sim to give us a more accurate evaluation of the circuit. When using the calculated turns ratio of 26.5, the output voltage across the resistor is 4.069 volts. This is too low, so the turn ratio was decreased to 23:1, increasing the secondary voltage and producing 4.935 volts, which is close to the desired 5 volts. One reason for the slight discrepancy is that the diode drop-in voltage for the maximum input voltage is slightly greater than 10 volts, rather than the assumed 0.7. The ripple voltage is approximately 0.1 volt, which is within the 0.15 volt specification. In the multi-sim simulation, a general purpose 1N4001 diode was used. This diode was chosen for its forward average current being 1 amp, its reverse peak current being at 50 volts, and its forward surge current being at 30 amps, all of which are below our design specifications. In order for the computer simulation to be valid, the diode used in the simulation and in the actual circuit must match. For this example, to reduce the diode voltage and increase the peak output voltage, a diode with a much larger cross-sectional area should be used.